In this lecture, I shall present Hess's law, and we will work through a series of Hess's law based example calculations. A thermodynamic system is described by a series of state functions. State functions are such that how the system came to be in that particular state have no bearing whatsoever on their value. This caused Germain Hess in 1840 to propose that the enthalpy change of a process is independent of the pathway between the initial and final states. What this basically means is that if a chemical reaction can be performed in one step or in a series of sequential steps, the enthalpy change for the single step process will be equal to the sum of the enthalpy changes of the sequential steps. Necessarily, by definition, this path independence holds for all state functions, and hence Hess's law is applicable to standard enthalpies of reaction, standard internal energies of reaction, standard entropies of reaction, and standard Gibbs energies of reaction. So, just to reiterate, the state functions that are most commonly questioned in Hess's law questions are enthalpy, internal energy, entropy, and Gibbs energy. A series of formal definitions of enthalpy changes for various processes exist, and these are listed on slides 4 and 5. I do not propose to read them out or go through them particularly, but you should spend a few minutes to familiarize yourself with them. It should be noted that each standard enthalpy has a symbol, and whilst there is some controversy over the symbols used, the ones that I have given here are the ones proposed by IUPAC. Okay, so all Hess's law problems require you to calculate a change in a given state function. You are invariably given some ancillary data, and that data will always allow you to construct an alternative pathway to get from the initial state to the final one. The alternative route that you construct will then have the same change of state function as the requested one. So let's see how the theory works as an actual calculation. So the task we are given is to calculate the enthalpy change for the combustion of propane in oxygen, which is given as the equation at the top, given the following enthalpies of formation. And we have enthalpies of formation of propane gas, oxygen gas, carbon dioxide gas, and water liquid. You'll notice that the enthalpy of formation of oxygen gas is 0 kilojoules per mole. This stems from the definition of enthalpy of formation, which is the enthalpy change for the formation of a substance from its elements in their standard states. Oxygen gas already is an element in its standard state. So in essence, the enthalpy of formation of oxygen is for the conversion of oxygen gas into oxygen gas, hence the enthalpy of formation is 0. So how do we go about solving this problem? We start with the equation that we've got to calculate the enthalpy change for. Underneath the equation, we write constituent elements in their standard states. So for propane and 5 moles of oxygen, the constituent elements in their standard states will be 3 moles of carbon solid, 4 moles of hydrogen gas, and 5 moles of oxygen gas. We then draw arrows from the constituent elements in their standard states up to the species in the actual equation. So going from constituent elements in their standard states to propane gas is the enthalpy of formation of propane gas. Going from constituent elements in their standard states to 5 moles of oxygen gas is 5 times the enthalpy of formation of oxygen gas. Going from constituent elements in their standard states to 3 moles of carbon dioxide gas is 3 times the enthalpy of formation of carbon dioxide gas. and in a similar fashion the final arrow is 4 times the enthalpy of formation of liquid water. The enthalpy change that we are asked to calculate is the enthalpy for the combustion of propane, which is given the symbol delta C H standard. We are asked to calculate the enthalpy change going from the reactants to products. But instead of going directly from reactants to products, we can go from reactants down to the constituent elements in their standard state. So in other words, we can dismantle the reactants, and then we can go from constituent elements in their standard states back up to products. So we can dismantle the reactants and reconstruct the products. How do we know that the atoms that we get, or the molecules and atoms that we get when we deconstruct the reactants, will make the products exactly? The answer to that is that the equation is balanced, so that must be the case. So if we consider our alternative route, so the enthalpy of combustion of propane is going to be equal to minus the enthalpy of formation of propane, minus because we are travelling in the opposite direction to the arrow, minus 5 times the enthalpy of formation of oxygen, again minus because we're travelling against the direction of the arrow, then plus 3 times the enthalpy of formation of carbon dioxide, plus 4 times the enthalpy of formation of water liquid. And if we total all of this up and are careful with our minus signs, we should get that the enthalpy of combustion of propane is minus 2,220 kilojoules per mole. Whenever you do a calculation like this, or indeed any calculation in science, always try to consider, is the answer sensible? So first of all, the enthalpy of combustion has turned out to be a negative value. That suggests that the reaction is exothermic, which is what you would expect given that propane is actually a fuel. And 2,220 kilojoules per mole is quite a large enthalpy change, again, which is what you would expect given that propane is actually a fuel. So the answer does seem sensible. Another way to look at this kind of problem is that if you are given a series of reactants from R1 through to Rm with balancing numbers nu1 through to nu-m being converted to products P1 through to Pn with balancing numbers nu1 through to nu-n, then in order to calculate the enthalpy change for such a reaction, it's basically the sum of the enthalpies of formation of the products, each one multiplied by its balancing number, minus the sum of the enthalpies of formation of the reactants, again each one multiplied by its balancing numbers. So this is exactly the same calculation as we had before, minus the enthalpy of formation of propane, minus 5 times the enthalpy of formation of oxygen, plus 3 times the enthalpy of formation of carbon dioxide, plus 4 times the enthalpy of formation of water. In actual fact, both of these methods are identical, it's just a slightly different way of approaching the problem. Okay, in this second example calculation, we're asked to calculate the change in enthalpy for the reaction given at the top, given a series of reaction enthalpies for a series of other reactions. The basis of questions like this is that it must be possible to construct the reaction written at the top from the reactions that are given underneath. So the way to do this is to look at the reactions and try to find a species that appears only once in those reactions. So for example, if we look at OF2 gas, the only one of the 3 equations that actually contains OF2 gas is equation 1. And equation 1 converts 1 mole of OF2 gas into products. Clearly, in the equation that we are trying to calculate the enthalpy change for, we need 2 moles of OF2 to be converted. So consequently, we need 2 lots of equation 1 to happen. If we look at equation 2, we see that equation 2 converts 1 mole of SF4 gas, and it is the only equation to contain SF4 gas. In the equation that we're trying to calculate the enthalpy for, SF4 gas actually appears as a product and not a reactant. So we actually need to perform equation 2 backwards, and consequently we multiply it by -1. For equation 3, we convert 1 mole of sulfur gas to products, and again this is the only equation that contains sulfur. We need to convert 2 moles of sulfur gas to products, so consequently we need 2 lots of equation 3. So in summary, we need 2 lots of equation 1, -1 lot of equation 2, and 2 lots of equation 3. Just to prove that this combination of these reactions does actually equal the overall reaction that we're trying to calculate the enthalpy change for, we need to do some reaction arithmetic. So what I've done is I've written the 3 reactions out, but I've multiplied their coefficients by the numbers that we just calculated. So I've written out double reaction 1. I've written reaction 2 backwards. That basically simulates the -1, so I've written the products on the reactant side and the reactants on the product side. And equation 3, I've also multiplied the coefficients by 2. What we then do is we add everything on the left hand side of the equations together, so we actually get 6 species, and then we add everything on the right hand side of the equations together. The next thing to do is to see if anything can be cancelled on either side of the equation, and we should hopefully see that there are 4 HF gas on the left and 4 HF gas on the right, so they cancel. There are 2 waters on the left and 2 waters on the right, so they also cancel. There are 2 oxygens on the left and 2 oxygens on the right, so they cancel. And there is 1 sulfur dioxide on the left, which will cancel 1 of the 2 sulfur dioxides on the right. Having performed all of this cancelling, we are left with 2 sulfur gas and 2 OF2 gas on the left hand side, and 1 SO2 gas and 1 SF4 gas on the right hand side. And this is the original equation that we had to work out the enthalpy change for. So we've now shown that our combination of the various reactions does actually indeed equate to the reaction that we need, and so now it's just a simple matter of multiplying the enthalpy changes for each reaction by the multiplying numbers that we calculated. So we need 2 lots of reaction 1, -1 lot of reaction 2, and 2 lots of reaction 3. And again, if we add all of this together and are careful with our signs, we should get that delta RH equals -320 kilojoules. Given these 2 examples, you should be equipped to perform the very vast majority of Hess's law calculations that should come your way.